The next topic that we're going to tackle here in Module 4 is from Section 3.2. We're going to be dealing with the law of cosines, followed by what's known as Heron's formula for finding area. This is going to contrast with our work with law of sines in that these particular law of cosines formulas are going to be used in different cases than what we saw before. I kind of mentioned it in Lecture 19 and in Lecture 20, but one of the things that we need to be really good at by the end of this module is identifying what given information determines which of our specific law of sines or law of cosine routes we want to go down. So we're going to kind of complete that set with our work today, along with some extra practice examples. As we kick things off, as always, we have a list of objectives for this section. We're going to start by looking at law of cosines to solve oblique triangles, but we're looking at the final two cases, the case where we know 3 side lengths, and the case where we know 2 side lengths and the angle included between them. Don't confuse that second one, by the way, with our work that we did previously finding the area of an oblique triangle. Specifically, we're solving triangles, which means finding all of their side lengths and all of their angles. We actually won't be touching on our second objective here, which would be to use law of cosines to model and solve real-life problems. And again, part of the reason for that is that these are just the same problems we'll be doing for Objective 1, but with a little bit of dressing to make them appear as application problems. So we're going to be skipping over that. The last thing that we're going to do, though, is use what's known as, again, Heron's area formula to find the area for oblique triangles. This one is a little bit different than the one that we had when we were dealing with law of sines, and it has just an extra little wrinkle that kind of complicates things. In my opinion, it can be easier, but it's really going to depend upon the information you have that determines whether you use this or the formulas that we had previously. It's all about what information you're given and the shortest path to success. With that out of the way, a short introduction on the work that we're going to be doing. One of the things that we need to kind of discuss is that while law of sines had a lot of different applications and usages, it didn't cover every single possibility for solving oblique triangles. The 2 cases that we still need to deal with are the case where we know all 3 side lengths, or again, 2 side lengths and an included angle. They mention here in this second little blurb that if this is the situation, 3 known sides or 2 sides and an included angle, none of the ratio in our law of sines would be complete. So we're going to switch and instead use the law of cosines. I want to do a brief aside here and actually show why this wouldn't work here. If we're taking a look at our law of sines, and we have a over sine of a equals b over sine of b equals c over sine of c, we can kind of see why this is a little bit of an issue for us. In the case of knowing all 3 side lengths, it's really obvious as to why we run into a problem here, because we won't have a single complete ratio to work with. In this case, I'll know A, B, and C, but in order to solve for these missing angle measures, I need at least one complete ratio to set it up in a proper proportion. But the same thing is true if we know 2 sides and their included angle. That would be saying that you know A and C and the angle between them, which is B. In this case, you run into the same problem. I don't have a single complete ratio in order to set up a proportion. If I know A and sine of B, I can't solve for either B or sine of A because I just don't have enough information for a complete proportion. As we talked about, a proportion works when we know 3 out of the 4 pieces of information, and we can then solve for the 4th. In this case, we just don't have enough to work with. So that's where law of cosines is going to come in and fill the gap for us. Law of cosines actually has several different forms depending upon what it is you're looking for. But it's important to note here that they all have the same basic pattern. So as you're looking at this table here, try not to get overwhelmed by the sheer amount of information that you're seeing here. Let me talk to you a little bit about what's going on in each case and the easiest way to commit these to memory so that you won't make mistakes. If you take a look at each of these, let's start with the standard form for a squared. Let's say that I knew the lengths of B and C, and I knew the measure for angle A. So this would be a side angle side triangle that I know. I can find the missing side length A by the formula a squared equals b squared plus c squared. That should seem kind of familiar because it looks a little bit like our Pythagorean formula. The only difference being that because we're not in a right triangle, we're an oblique triangle, we have an extra piece added on. Minus 2 times b times c times the cosine of a. And now you see why this is called the law of cosines, because this particular formula uses the cosine of the known angle. Now, if we look at the other remaining standard forms, you'll see the same pattern each time. To find the missing side length, we take the sum of squares of the two known side lengths minus 2 times their product times the cosine of the known angle. So a squared is b squared plus c squared minus 2bc times cosine a. B squared is a squared plus c squared minus 2ac times the cosine of b. C squared is a squared plus b squared minus 2ab times the cosine of c. Always the same pattern. The sum of the squares of the other two sides minus 2 times their product times the cosine of the known angle. The alternative forms on the right-hand side are the exact same equations, but this time they're solved for the angle instead. Specifically, the cosine of a is b squared plus c squared, so the same thing, minus a squared all over 2 times b times c. Basically what happens is you add 2bc cosine a to both sides, subtract a squared, and then divide by 2bc. So in this case, you also have a pattern to work from. Cosine of a is the sum of squares of the other two sides, the sides that this angle is between, minus the square of the side opposite, all over 2 times the adjacent side's products, so 2 times b times c. In reality, to know all 6 of these forms, you only need to memorize one equation, and then know the patterns. If you could memorize a squared equals b squared plus c squared minus 2bc times cosine of a, you can rework it to find the alternate form, and you can swap out the side lengths to find the other remaining parts. When would we use the alternative form, by the way? We mentioned that standard form is used in the side angle side case, when we know 2 side lengths and the measure of their included angle. The alternative form is going to be used when we're dealing with a side-side-side triangle. When we know all 3 sides of the triangles, the first thing that we're going to do is find one of the angles, and once we know that, we're actually going to proceed with law of sines. And we'll talk a little bit about why that is, and we're also going to talk about which angle you should actually be focused on solving first, because it's going to be very important that we do this correctly, otherwise we're going to take a pretty severe misstep.